Boeing is crashing and burning, both literally and financially, with more than $32 billion drained away since 2019, a staggering downfall for a company once considered untouchable in the aviation industry. While Boeing struggles to keep its planes safely in the skies, Elon Musk has stepped into the picture and casually dropped a bombshell that could change everything. With his signature confidence, Musk revealed that he has already designed an electric supersonic vertical takeoff jet, a concept that once sounded like science fiction, but now seems frighteningly close to reality. He admitted that it is an entirely new product with completely new systems, new challenges, and new approaches, but then casually remarked that success would mean producing even half a projected 10,000 aircraft. That statement alone stunned listeners because it implied Tesla's bold ambition of eventually deploying 10,000 electric planes, while Boeing is still patching up safety concerns. What gave Musk this audacity to believe Tesla could succeed where decades of aerospace giants have failed? The answer lies in the revolutionary design of the 2026 Tesla super electric plane, a project that is officially on the horizon and ready to shock the entire aviation industry. This aircraft is built to achieve a jaw-dropping 1,500-mile flight range, using a compact electric vehicle-inspired tail design, while simultaneously overcoming the almost impossible hurdles of FAA regulation. These breakthroughs were long considered unattainable, yet Tesla is proving them possible right now, forcing engineers, regulators, and competitors to rethink what the future of aviation looks like. The story of this transformation begins with a simple but game-changing question. How can metal as common as aluminum end China's dominance in the battery industry and give Tesla an edge in electric aviation? At first glance, Tesla's short wings shouldn't allow their aircraft to travel very far. In conventional aeronautical wisdom, longer wings are required for greater lift and efficiency. Yet Tesla's electric plane has been engineered to travel 1,500 miles, defying not only physics as we understand it, but also the long-standing designs of companies like Boeing, which rely on massive wingspans. To understand how Tesla has done this, we need to look at one of the most sacred principles in aviation engineering, the Breguet range equation. For decades, this formula has been the holy grail of aviation efficiency, used to calculate the range of aircraft based on specific fuel consumption, lift-to-drag ratios, and the changing weight of planes as they burn fuel. For traditional fuel-powered aircraft, this equation makes perfect sense. Jets begin heavy with fuel and gradually become lighter as they burn it, which directly affects their efficiency and range. But Tesla has rewritten the playbook. Because electric aircraft don't burn fuel, they don't shed weight mid-flight. A Boeing 737 might burn through 50,000 pounds of fuel during a long-haul journey, whereas Tesla's design maintains nearly constant mass from takeoff to landing. This changes the mathematics entirely. Tesla's engineers can work with far more favorable numbers because the logarithmic portion of the Breguet equation that normally penalizes aircraft weight changes does not apply in the same way. Add to this the fact that Tesla's electric motors boast efficiencies of up to 95% compared to a meager 40% in traditional jet engines, and suddenly the equation tips strongly in Tesla's favor. In practical terms, Tesla's electric aircraft achieve specific energy consumption as low as 0.15 to 0.2 pound equivalent per pound per hour, while conventional jets remain stuck between 0.5 and 0.7. This alone represents a seismic leap in efficiency. But Tesla doesn't stop there. Tesla's engineers have also dramatically improved the lift-to-drag ratio. While most commercial jets hover around a 17-to-1 ratio, Tesla is targeting an astonishing 25-to-1. That's a 47% improvement in aerodynamic efficiency, which directly translates to hundreds of extra miles of range. How is this possible on a smaller wing? The answer lies in distributed electric propulsion. Tesla's wing design spans only 50 feet, much shorter than the Boeing 737's 93-foot wingspan, yet it incorporates between 8 and 12 motors along its surface. This setup created a phenomenon called the blown wing effect, where air is accelerated over the wing by distributed propellers, increasing lift by 50% while simultaneously cutting induced drag by a quarter. Effectively, the compact Tesla wing performs as though it were twice its actual size. On top of this, Tesla employs advanced carbon fiber composites to reduce wing weight from 1,000 pounds down to just 600 without sacrificing structural integrity. This reduction in weight allows for a higher effective aspect ratio of 10:1, which makes the wing aerodynamically behave like a much longer structure. Furthermore, Tesla integrates variable geometry technology, meaning the wings can adjust themselves mid-flight. This dynamic configuration reduces parasitic drag by as much as 38% when the propellers retract during cruise, optimizing the plane's performance at different stages of flight. In simulations, this design has proven capable of achieving a total drag coefficient of just 0.25, significantly better than the 0.3 coefficient common among rivals. Feeding these numbers back into the Breguet equation reveals something astonishing. Tesla's design can extend range by another 20 to 30% beyond conventional expectations. In practice, the Tesla electric plane consumes only the energy equivalent of 20,000 pounds of fuel to fly 1,500 miles, compared to Boeing's 50,000 pounds of fuel for just 500 miles. This scientific breakthrough is not mere theory. The numbers, wind tunnel experiments, and simulations all tell the same story. Tesla's compact electric aircraft design could slash up to 500 million tons of annual carbon emissions, deliver jet-like range and endurance, and do it all while incorporating vertical takeoff and landing agility. It's a blueprint for not just competing with Boeing, but potentially ending their dominance in aviation altogether. Imagine an industry where aircraft are lighter, safer, quieter, and dramatically more efficient, all powered by sustainable electricity. That is the future Tesla is aiming to create. But one of the greatest obstacles Tesla faces is not physics, it's regulation. The Federal Aviation Administration, FAA, is notorious for strict rules governing pilots and aircraft certification. Under Part 135 regulations, every commercial flight must be operated by a certified human pilot with at least 1,500 hours of training. The FAA enforces these rules because aviation accidents are catastrophic, and its threshold for safety allows only one catastrophic failure in every 10 million flights. These are not arbitrary numbers. They exist because tragedies like the Boeing 737 MAX crashes, which killed 346 people, have proven that even small flaws can cost hundreds of lives. For Tesla, breaking into aviation requires not only technology, but also convincing regulators that their system is safe. Tesla's strategy here is nothing short of brilliant. Instead of fighting the FAA, Tesla is gaming the system legally by first certifying under Part 91 experimental testing, essentially operating with a learner's permit. This allows them to accumulate vast amounts of real-world flight data before moving into commercial space. At the same time, Tesla benefits from recent FAA efforts to streamline certification processes for electric vertical takeoff and landing aircraft, a policy shift already helping companies like Joby Aviation. With timelines for certification dropping from 10 years to as little as 2 or 3, Tesla is entering at exactly the right moment. The ace up Tesla's sleeve is data superiority. With over 10 billion miles of autopilot driving data already collected, Tesla can demonstrate error rates of just 1 in a billion operations, compared to human pilots who statistically make errors once every 100,000 operations. Tesla argues that their AI systems don't suffer from fatigue, distraction, or emotional decision-making. However, they are not eliminating human oversight entirely. Instead, Tesla envisions a hybrid model where AI performs most of the flying, while remote human pilots monitor operations through Starlink satellites with latency below 100 milliseconds. This setup satisfies the FAA's requirement for a pilot in command without needing that pilot to physically sit inside the cockpit. It's essentially Uber for the skies, but with safety redundancies designed to exceed the FAA's reliability standards. Tesla's AI has been engineered to handle emergencies faster and more precisely than any human. Where pilots react within 1 or 2 seconds, Tesla's AI processes inputs in milliseconds, analyzing over 1,000 variables every second. During an engine failure, for example, multiple redundant neural networks cross-check optimal glide paths to the nearest safe landing spot, maintaining precise descent rates of 500 feet per minute. On top of this, human pilots on the ground can step in instantly if necessary, giving Tesla's system the best of both worlds. AI precision with human oversight. Transparency is another weapon Tesla wields. Unlike traditional black boxes, Tesla's AI provides real-time logs explaining every decision, from altitude adjustments to turbulence avoidance. This level of openness is designed to build trust with regulators and passengers alike. When you put all of these pieces together, the revolutionary wing design, unmatched energy efficiency, regulatory strategy, and safety systems, it becomes clear why Tesla's 2026 super electric plane is not just a product, but a turning point in aviation history. Boeing's dominance looks increasingly fragile as Tesla positions itself to own the skies. The question now is whether Boeing can adapt to survive the storm, or whether we are witnessing the dawn of a new aviation era led by Tesla.